Oh, welcome to the third lecture of this course. And before I started, I wanted to, felt after I finished the last videos that I forgot to do something with this adaptive optics. So to show you why it is worth to put all this effort in to have constantly changing mirrors, constantly trying to improve the quality of the picture, basically taking so many pictures all the time and then adding them up. Well, and here what you see, oops, here on the right hand side, this is Neptune. This is taken with the very large telescope without corrections, without this adaptive optics. Then we send the Hubble Space Telescope into space, don't have the disturbance of the atmosphere. The mirror is about only a tenth of the very large telescope, which is one of these in Atacama at the European Southern Observatory. And the credit for these pictures goes to them. And we see already details. We see there is something going on the poles. And there seem to be this white stains, whatever, which turns out to be storms. But now we switch on in the very large telescope. This adaptive optics use that it has much bigger mirrors, and we correct now for the disturbances in the atmosphere. And we get a picture on the quality that is shown here on the right-hand side. And we see, well, it's not at the same time taken. So these are different storms, but we still see this band of storms that seemingly was already seen by Hubble, but with a bit better resolution. So we get a better quality. Now, this is at the bottom, this is a simulation. This is a nebula, what means some kind of region with enhanced dust or gases density in our galaxy. It's called the NGC 3603, so New Galactic Catalog 3603. And left is the Hubble Space Telescope, the quality of the picture. Then this is the very large telescope plus AO. I should have looked up what is AO. So again, adaptive optics plus AO, adaptive optics. Stupid me. Okay, learn something. And we see already the quality that this cluster of stars here is better resolved. So we see finer details. And then this here is a prediction what the ELT, so extreme large telescope that is in construction and hopefully will go online 2026. I don't know how construction projects are in Chile, but in Germany it would be projected 2026, and then one could make a time to completion or time and plot time to completion, and this is usually then some kind of parabolic behavior. Okay, but I just wanted you to show this advantage of adaptive optics. Use this laser beam, make a fake star. Use your optics correct for any disturbances, and you get a better picture, a far better picture. Or one sees the influence basically still of the atmosphere on pictures. So even if you go to 4,000 to 5,000 meters height, where the atmosphere is far less dense and less polluted and whatever. Oh, okay. So, but now let's come back. So this was the optics. Basically, if we look out into space with different eyes and different wavelengths. Now today I want to go a bit more about the gravitational force. So lecture 3. Space, what is it? To give you at least a feeling I can't properly explain it because I don't understand it by myself. I have to be so honest. I understand a few of the concepts, or I get a feeling for a few of the concepts, and hopefully I can pass this on, but really, truly understanding. Oh. Well, and then, of course, go basically to a monumental breakthrough in astronomy. This is like if you have been born seeing, but deaf, and suddenly you get ears. Wow. So the central perception gets much, much richer. You see objects, but now suddenly you might even hear some kind of bang. It's a dangerous comparison because sound is the compression of air, basically make the number of molecules and regions denser. While what we talk now, this gravitational waves, is rather distortion of the underlying space, of the geometry that is underneath or surrounding us. It's a bit dangerous, but nevertheless, you will see we have to deal with frequencies, and frequencies can be nicely taken over to sounds. So, and this is for me quite a nuisance, these gravitational waves. Well, in 2015, we could talk of them. Yeah, people try, and that's the method they try. Then was discovered, and since then they are so rapidly improving their sensitivity that I hear more and more, and they're so successful. Every year I have to update basically the number of observations drastically. So let's go on and start with basically the first guy who really, well, he was certainly not the first one, but the first one that gave us a mathematical description of the force that keeps everything together, gravity. So what keeps everything? Gravity, and gravity is a force that basically, if it wouldn't be there, what would happen? There would be no orbiting stuff. Right now the Earth is by gravity bound to the sun. Of course, it also Newton, actio equals reactio, or action equals reaction. What means the sun is pulling the Earth, but the Earth is also pulling on the sun. It's just that the sun is so much heavier. It's like an ant pulling on the elephant, or the elephant is pulling on the ant. They are connected somehow by a rope. Well, if this wouldn't be there, when I was a kid, my mom always sent me down the road to the farmer to get the milk in the evening, and then we have the can. And at some point, the little boy realized that if he makes loops with the can, he doesn't spill the milk. You try to do it faster and faster, and at some point, the handle breaks. And then the milk can flies and hammers on the street, and the entire milk is on the street, and the mom gives you the good old pedagogical treatment with a slap. Nowadays, no longer allowed. Okay, that's how I discovered in the moment there is no force anymore, an object will go straight on. Well, by the way, the Earth is constantly moving with about 30 kilometers per second, which is quite something. So if there wouldn't be any force, it would go straight on. So there must be some kind of force. It's working on the planets in our solar system. The sun is so much the mass, 99.9% of the mass in the solar system are bound in the sun. So this is the dictator. Everything else moves around it. The others, of course, also pull a bit on it, but it just makes a small dance compared to the others. Of course, then one star is the other star, is the other star, is the other star, and the galaxies. They have unusual. We have to sum up basically their overall stars, and then we find one common center of gravity, and very likely we find in this common center of gravity a massive black hole. with a couple of million times the mass of our sun. That keeps all together, but we're later going to see that what we see in Mars is not enough to explain the orbiting of stars around the galactic center. Comes in later. So we have some kind of gravitational force. There is no discussion about. And then Newton, well, would say that force equals the mass multiplied with acceleration. So we have there two things entering, the mass as well as the acceleration. Or the mass is a measure how inert is a body towards changes of a state of motion. And on Earth, it turns out that this acceleration A, we would write down with lowercase g, which turns out to be 9.81 meters per second squared. It's not a universal constant. This is just a more or less hand-waving approximation. It even changes on Earth. Makes a difference whether you are on sea level or whether you are on 5,000 meters in your observatory. It already starts. So, but nevertheless, it's a good approximation that the gravitation that binds us to Earth is about m times g. Your mass multiplied with g, that's how a scale works. So that is one thing. But now we all know this famous picture. There was some kind of a lockdown in London or Oxford, and or was in Cambridge. There was a lockdown, and Newton had to stay on the countryside. And obviously, as physicists, you can do work even by sitting underneath an apple tree. And the apple fell on his head, the old famous story. And that gave him this eureka moment that gravitate is basically one mass attracts the other mass. So we could also say that the apple stays straight on and the rest inertial system moves, but the apple stays at rest. We just changed the reference frame. But obviously, so also the apple would also, with the same force, attract the Earth. But the Earth is, of course, too inert to that its motion or its forces to be recognized. So Newton had then the idea that one mass attracts the other mass. And this is proportional to the square of the distance between these two. So it means if you go further away, the gravitational force that one body attracts you is dropping. If you go twice as far away, it's only a quarter. If you go 3 times, it's only a 1/9. Whoa. So this common law, he made basically this proportionality. And now the nature of physics law again, we establish a proportionality. So the force is proportional to one mass multiplied with the other mass divided by r, the distance squared. Okay. Yet if we want to calculate something, we want an equal sign. We see now we have here Newton, which is kilogram meter per second squared in terms of units. Here on the right, we have kilogram multiplied with kilogram. So kilogram squared divided by meter squared. Already that doesn't fit together with the units. But then it depends, of course, the unit system. We would use standard international with meter, second, and so on. There used to be also other ones, or the UK, you have this imperial system, with yards and acres, stone, and whatever stuff. So it depends on, but nevertheless, in order to have this right between left and right, we need to introduce a constant. which takes care of the numerical values as well of the units. This turns out to be here the gravitational constant G. This is something, this G, we would assume is universal. That gravity on the other side of the universe is the same as in our section. Wow. So everywhere in the universe, we would expect this G to be the same value. And if we measure it, it turns out something, a very small number, 6.67, 10 to the minus 11 Newton meter squared, kilogram squared. If this is a small number, means that in order to become gravity to be sizable, this product here, or at least one of these factors here, needs to be sizable to really make a big change. Theoretically, you could put one marble and another marble on the table, and then there works gravity between them. And then you could measure how you. The problem is that even the friction that works on this sphere to get them moving is higher than this gravity. So the system stays at rest. It's because gravity is such a weak force. A stronger force is the Coulomb force between charges, positive and negative charges. If we take all electrons in a penny, bring them to the moon, leave the positive charged nuclei on Earth, the force would be so large that within a couple of seconds, Earth and moon would crush into each other, because the force would be so dragging them towards each other so strongly. We're talking about 380,000 kilometers, so quite something. That is a proper force, while gravity is so to give you a feeling. Nevertheless, we have the Newton's gravitational law. The gravity between one body m with the mass m and the other body with the mass capital M equals G, the product of force, and the distance of the square. So this leads us to the question, why do we have on Earth G times M? But in general, we have capital G, capital M divided by R squared. Obviously, this mass of your body is still the same. Well, if we look at Earth, it has a certain radius, so this here, which is relatively constant. It's so big, 5,770 kilometers as radius. If you have +5 or -5, and you dive for +10 and -10, the change is less than a per mil. What is a per mil as long as it's not alcohol in the blood? So, okay, then the Earth's mass, 10 to the 24 kilograms. Oh, that is sizable. Even compensates for this 10 to the -11. So we have here constant, here constant, here constant. But this is what we can take now and calculate together as one small constant minor G. So then we see, obviously, if we change this R, this has slightly an effect. Therefore, it's not a universal constant. And on Moon, for example, Moon has, I think, a 1/6 of the mass, but also just a third or so of the radius. It turns out that you have only, I think, a 1/6 of your weight if you're on the surface of Moon. Well, it's smaller, so R squared is smaller, and therefore the force would be higher if you would have the same mass, but the mass is also drastically smaller. so if you want to slim down, just take your rocket. If you're a billionaire, have yourself a rocket build and fly to moon, and stand there on the scale and then fly back. Of course, you could invest also the money to feed starving people, but obviously it's more fancy to fly to the moon, into space. So this is basically, if you take these numbers and multiply them out, we come down to this 9.81 meter per second squared. Okay. Yet Newton has one problem. It's basically, usually you need some kind of rope or something that mediates these forces. One could make a force field and gives basically every point in space a force per unit mass. That would be the gravitational field according to Newton's mechanics. Oh, so you make it basically from this distant interaction to a local one. But Newton has, for example, one problem. If the sun disappears, immediately the force disappears and you fly out into space. Earth flies out into space. There is no, it's basically, it doesn't take into consideration that this information has to travel a distance, an astronomical unit, or 8 light minutes. Okay, so this is somehow not really nice, because somebody else came along and said, which is the very basis of the theory of relativity, to say no information force field travels faster than the speed of light. So if the sun would disappear, until we would know it, would take 8.3 minutes, or what it is 8 light minutes, until we would realize, oh, the sun is gone. Crap. So this is a very basic assumption, that no information travels faster than the speed of light in vacuum. So, basic assumption. Therefore, Newton has no problem. This is a distance interaction, which is not transmitted. By the way, quantum mechanics would do it now that the force is nothing else than change of momentum. That means the state of motion. In order to change the state of motion, you usually need to apply a force. And this is transmitted via exchange particles. And the one for gravity would be called graviton. It should have been massless. The grab is we haven't found it. The exchange particle for the electromagnetic interaction is the photon, the light particle. This would be another description. But yet we want to go here for Einstein, who says that gravity is a completely different concept. So his theory, well, there's the special relativity, where you basically have just motions along a straight line relative to another observer at rest. And there's the general relativity. There it turns in that rotations come into game, and immediately this is, if you have nice motion along a straight line, this is usually Euclidean mechanics, and then it transforms via what is called a Lorentz transformation. That is still handleable even for limited mind like me. But in the moment you have rotations, and then you get curvilinear coordinates, and nasty. Okay. So this would be then the general theory of relativity. And between this publication, there was 1905, the special, and the general relativity was published 1915. Obviously, Einstein settled over from Germany to Switzerland, and Switzerland you could work 1915. You were not so busy hanging around in France or in Flanders in the mud. Okay. So now what does it take? Albert's brain that you see here, nicely Albert's brain preserved. I find it a bit obscene, honestly, to preserve dead bodies, but well, obviously some people think that this structure here has something to do with the ability to think. Yeah. So you take Albert's brain and loads of mass, differential geometry, mostly, and then you end up with what is called Einstein's field equations. No worries, no worries. This is just to show you how this equation looks like. Essentially, what we have here is the Ricci curvature tensor, which essentially gives us the properties of geometry of space, how bent it is, how twisted, and minus something, a scalar. This Ricci curvature tensor is basically a 4x4 matrix. Nothing more. But in this, there enters then some derivatives that give us the change of space, or the second derivative. Curvature of a function is always related towards the second derivative. This goes with is then combined with a scalar curvature, which means just a number, multiplied with the metric tensor. And the metric tensor gives us the geometry of space and how it transforms from one coordinate system to another. In math, you're soon going to learn about the Jacobi matrix and Jacobi determinants. Well, if you take this Jacobi matrix, which is the derivative, if you go from one coordinate system to another, of the set of one coordinate in the first set for the coordinate in the second set. So if we have polar coordinates, x equals r times cosine phi, the x, the r would be the derivative of r cosine phi for r. That means cosine phi. This would be one entry. That's basically what is then entering. And the product of the transpose of the Jacobi matrix multiplied with Jacobi matrix, this is the metric tensor. Then Einstein introduced the term. So this here basically describes us the geometry of space. How is it? If you go basically, if you take a map, and not only a map, if you take a relief of a mountain range, you get basically in the valley, you have a thing, you put a ball in, it will stay there, there is no force acting. If you take it on the steep slope, it will be a big force acting. So this is basically the geometry of space. Then Einstein introduced another term, what is called the cosmological constant, multiplied again with this metric tensor. And this equals on the right-hand side some constants where the even the gravitational constant again enters. D to the power 4, the speed of light. You will always have speed of light in this equation, usually square of speed of light. E equals m, or E is proportional, the energy is proportional to the mass. Now we want an equal sign, so we need a proportionality factor, and it turns out to be the speed of light to the square. The laws of mass or of physics. We establish a proportionality, and then we need in the experiment to determine the proportionality factor. Of course, you can also start calculation from first principle and try to figure it out. And if it agrees, you have a good theory. At least there is one theoretician in nuclear physics, Wojtek Nazarewicz, which is unbelievable. He's scientific director of the FRIP project, which is a $1 billion investment. And Wojtek, when he gives a talk, he likes to say, every theory is wrong. It's just a question to which degree is it wrong. Because usually you cannot model the entire complexity of the universe in a smaller system. There will be always something that you cut off, that you neglect, that you truncate. So, okay, but here you see we have G, we have C to the power 4 involved. And we have this stress energy tensor. There is basically the pressure going in, pressure and force per areas or something again. Force along the way, this is nothing else than energy. So all the energy, and don't forget, masses are directly proportional to energy. Masses also. Mass, this basically describes the effect of a local energy density onto the geometry of space. Oh. Well, Einstein was a very conservative guy. God doesn't throw the dice. So he's a rejection of quantum mechanics, basically a bit the statistical nature. But God throws the dice. It comes out from quantum statistics or from quantum mechanics, the inherent uncertainty. He also believed in a steady state universe. It was created and then it stayed basically with only small changes, but the big structure stayed. So yet he was also a cautious man. In case there is something changing, that the universe would expand or contract or something, you need some internal pressure or some force that works to the outside, some force that works from the outside to contract or from the inside towards the outside. So introduce basically this cosmological constant, and then basically rejected it. Yeah. Well, but to give you a feeling about this change of geometry, in the theory of relativity, this when you, for example, move very fast through a resting frame, I would recommend you here to stop, copy this link into your browser, then you will come to a website which nicely shows you effect that come because no information travels faster than speed of light. The speed of light is a constant. It doesn't matter in which a reference frame you are, in a moving one or in a resting one, the speed of light is the same. And with this, you can make now the transformation formula. Okay, so and if you do so, you see the effects on the geometry around you when you move fast through a system. And this is nicely shown here. It's basically a cyclist, and the speed of light is 30 kilometers per hour. 30 kilometers per hour, at least downhill, we all can manage. And then what happens with when you cycle through one of these medieval towns like Tübingen, which is southwest Germany. So obviously I come from this area. Together as Rangnick, Klopp, Tuchel. Yeah. Okay. To name a few of the most famous contemporary, most famous guys. And another guy, Einstein. He was born there, but then was not even a year old. And his parents settled over to Switzerland, Zurich, which is obviously southwest Germany, just around the corner. Okay. So if you cycle then through this town and you approach 30 kilometers per hour, so the speed of light, you will see the roundness of geometry, how everything becomes rounder around you. What you don't see, but basically because the light, in order to travel to you with 30 speed kilometers of hour, you cycle already. It basically almost, it comes from behind already. You can see behind yourself. So on this website, you also find a few sketches illuminating these effects. So if you want to go beyond, have a look. I certainly would recommend you have a quick stop, look at this video. I will now continue because what I have realized, I would now show you this video, waffle, but this disturbs your pleasure in watching it. And when I upload this later on a platform, the platform goes through and complains then about copyright. So no more videos in these videos. Sorry about this. I just give you the links. Well, this has been made. The credit goes here to a guy called Hans Ruder. Brilliant theoretical physicist. So absolute brilliant, and also a very good communicator of science. And because Einstein was born in my state and the state made a big advertising campaign, we can do everything. So even a theory of relativity, and then they made an example, which was wrong. So Ruder wrote to the Prime Minister, sorry, but your example is wrong. Obviously, you can't do everything. Even then, marketing campaign, guys that did it, made another example, went even to a university in Berlin, a new statement on, was wrong again. So Ruder wrote again to the Prime Minister and said, stop this shit. And they stopped it. Oh, excellent man. But also as human being, what you're going to realize is the people that are really, really good what they are doing. These are usually very approachable people. Only the ones which are insecure because they know they are fake. Often they stay away, and the really good people might usually take time and help people. And he was one of these guys. Unfortunately, 2 years ago, he passed by. Well, might be, you see him sitting here in the wheelchair. Polio. So one of the last victims of polio. But in his own sense of humor, he always said that was my strength. I would have liked to play football, but I couldn't. So I sat at home and did learn math. Oh. So a bit of a great mind that unfortunately 2 years ago passed by. So, and since we are still suffering from basically from a virus, polio, how many people were affected of this? The entire planet. 2020, when we were all whinging about the coronavirus, certainly loads of people were dying of it. There was also a success which was never really communicated. Africa eradicated polio. Only in parts of Afghanistan and Pakistan, polio is left on this planet. So we another succeeded in another eradicating another species. But hopeful for the coronavirus that maybe one day at least we get it so much under control, we can neglect it. Okay, back from this excursion then here to Einstein and his cosmological constant. So introduce, in case there is physics, expanding physics he doesn't know. So this was basically safety. Later on, he said that cosmological constant, the biggest blunder of my life. Well, he said it rather in German, Eselei. An esel is a donkey. Oh. So that was my donkey action of the life. Yeah, but we later, when we talk next or 2 weeks about the evolution of the universe, you're going to see it might have been not so stupid. So just in case. So essentially all this relativity stuff, we have now a different concept of space and time. Space and time are linked even together via velocity, distance per time. We can now introduce a fourth dimension. We usually have x, y, and z. In space, normal space, we have also a couple of abstract space. And if you do string theory, you have 28 dimensions or whatever. And other philosophies. So, but we usually have our 3 coordinates, and if we transform them to spherical coordinates, we still have 3 left. Except we have a symmetry, then we can slay 1. And now we want to have a 4th dimension that considers time. But time is given in seconds. Now, if we multiply time with a velocity, which is given in meters per second, the seconds cancel away, and we basically end up with, again, the dimension of a length. So this product, speed of light multiplied with time, gives us another 4th dimension of length. Well, time and space are now interlinked. This is something, maybe I should do it quickly. Where do I have to do it? Can I write here? Oh, let's, we hope. No. Oh, this again, trapped. Okay. So let me quickly look this down and give you a feeling for what are these effects between one reference frame and the second reference frame. So where is the, okay, tablet software, and hopefully it works. So you are in a spaceship. That travels with a given velocity in this direction. Now what you do, you make 2 mirrors and insert in this mirror a light ray that starts to resonate. So travels all the way. If here given distance, let's call it d, it travels with the speed of light, c. That's what you see when you are in the spaceship. Probably this drawing is now a piece of modern art, and you will find it next year in the Tate Gallery. Oh, okay, so what we have is basically this resonating stuff. So now you have the observer at rest that sees this system here. So what happens is basically this light ray is not resonating at the same place. It's resonating. It's moving while resonating. It's still, the velocity is the same, but if we consider this here, this is d, the distance between the two mirrors. We have here v times t, the distance, velocity multiplied with time. So here we have c equals d over t, or t intrinsic. T intrinsic is basically d divided by c. Now we have here t observer at rest. And obviously the light travels now a longer way, which is given as, according to Pythagoras, e times t squared plus d squared t observer squared, so from the outside. So, and the way, that is the way we see it travels with the speed of light divided by t observer. Now we could basically resolve this for v over c, and then we get a relation between the intrinsic time and the observing time. But since the speed is light is the same, but it travels now a longer way, seen from the observer, obviously the time inside this moving reference frame seems to progress slow, seen from this reference frame here, or from this moving out. Here the time seems to go a bit faster. Strange things. This is just because here's the way no longer, obviously. So according to Pythagoras, we get this component here on top. Then in the moving frame, where we just have d as resonation. The only explanation, if c is the same, the speed is the same, but you have suddenly to go a longer way with the same speed. The time takes over. So time in here seems to progress slower, smaller than t observer at the rest frame. This is this old twin paradox. So one twin here, the other twin goes on the spaceship, and relative to this one, the time on the spaceship progresses slower. And when he returns, his clock is a bit behind compared to this clock. This has been shown. Put an extreme precise clock on a plane, fast-moving plane, have the same clock at the ground, fly around till the tank is empty, come back, compare the clocks. You see a difference. Essentially, and you have outlined the way how to connect the systems. Enough of me struggling with mass. That was now just spontaneously, that wasn't really prepared. I should have thought this beforehand through. But it's basically showing you nicely these effects come. If we have finite speed of light that is the same in each system, each reference system. And you have seen this was already just a straight-on motion if there would be a circle. Oh, God. So, and we have now this fourth dimension of space-time. So, up from current slide. What this concept is basically saying here is energy stress tensor. Energy equals mass, or mass equals energy, and that causes a deformation of the space. This is then often shown on the geometry of space, that if we have a mass, it introduces a curvature, and we get a completely different coordinate system. Well, you can basically say also energy was energy stored. Oh. By the way, is still need to share, of course, again. Probably I forgot to show. Oh. Up. Okay, so mass deformed space. This is then one of these big things, that here the geometry is depending on the local presence of energy. And in deformation, there is, of course, also energy stored. Should not forget about. So, well, it really is in deformation energy stored. Just take a rod or some and try to bend it, and then you let it go, and you see it bouncing back. So there must be some energy stored, the capability to perform work. Same twist a rod, it will bounce back. Oh. There must be energy stored, the capability to make work, to make something moving. And the same is obviously then here. If you take away this mass, what will happen? The sheet will bounce back and try to adopt the geometry, but then go first vibrate around the equilibrium distribution or equilibrium position. It's the same as if you take a stone and throw it into water. You will then get, while the stone dives in, not before, not afterwards, you will now have basically the surface disturbed. And this is now communicating via a certain speed, the phase speed of the wave with the environment in these concentric circles. Then also you see that the intensity is proportional to the circumference of the circle. Or if it would be in the 3-dimension, it would be a sphere. And therefore, they're proportional to the surface of the sphere, which is proportional to the distance squared, 1 over r squared. Aha, suddenly we have this 1 over r squared motivated. So basically, gravity becomes now a property. Gravity is some kind of local energy density that deforms space. So gravity is now a property of the geometry of space. We have the Earth that deforms space, and now we have a moving particle called Moon that is orbiting here around. And it orbits because there is no friction. It's like a marble. You put in a marble run and let it. If there's no friction, it will be always on the same orbit. With the moon, that's not true, because we have learned that the moon stopped the intrinsic rotation the revolution, well, what happened? Somehow, somewhere this energy had to go. So it went into the basically the speed, and it slightly drifted away, but surely drifted away from the Earth. In fact, it still drifts away, the moon still drifts away from the Earth, and one day we might lose, the Earth might lose Earth's stop of rotation. It's a couple of centimeters, I think, even per year. So, and when the moon was created, it was very likely only a couple of tens of thousands of kilometers about the Earth. So if the moon was over you, it was massive, massive. But also the tidal forces it had on the Earth or the oceans was not about only a few meters. This was a couple of tens of meters. So the moon, basically, it follows its straight line, but since space is bent, it stays on this equipotential line and goes in circles. And now I would like to make a break here, because first of all, my coffee is coming to an end, and I'm not sure whether I have had shared or not shared. This is not crucial, whether I keep this video or whether I have to start it and re-record it. Okay. Stop share and stop recording. Sorry about this, but what the photon and the massless particle does with this geometry, let's see.